Welcome back, everyone. I am so incredibly excited to have you here for today's explainer. If you're the kind of person who loves looking up at the night sky and just wondering about the hidden dynamics of the universe, well, you are in exactly the right place. Today, we're taking a mesmerizing journey into the Perseus constellation to explore a seriously rare astronomical phenomenon known as Caldwell 14. So let's just dive right into it.
Long before we had these massive space telescopes or any kind of complex data, ancient astronomers just looked up and saw these two brilliant, hazy patches of light in the northern sky. In Greek mythology, these naked-eye clusters were beautifully described as the jeweled handle of Perseus's sword. It's a wonderfully poetic description for what we now know is a literal powerhouse of stellar evolution.
But to really appreciate what we're looking at today, we have to grasp the massive scale of it all right up front. These twin jewels are located, on average, 7,500 light-years away from us, sitting deep inside the Perseus spiral arm of our Milky Way galaxy. To put that into perspective, the light hitting your eyes when you look at them tonight actually began its journey before recorded human history even started. Absolutely mind-blowing.
Okay, here is our flight plan for the explainer today. 1. The Jewels of Perseus. 2. Meet the cosmic twins. 3. Inside the stellar cores. 4. Revealing the hidden halo. And finally 5. The future of Caldwell 14.
All right, Section 1. The Jewels of Perseus.
So when we gaze at Caldwell 14, what exactly are we looking at from an astrophysics standpoint? Well, it's what astronomers call a binary open cluster, or a BOC. Now, most open star clusters, which are basically just groups of stars loosely bound by gravity, they're found wandering the galaxy totally alone. Finding a binary open cluster is incredibly rare. It means we have two distinct clusters that actually originated from the fragmentation of the exact same giant molecular cloud. And because they share this identical birthplace, similar ages, and are right next to each other in space, they serve as these perfect, naturally occurring cosmic laboratories. They literally let us test theories of stellar evolution by comparing how two populations of stars evolve side by side in the exact same galactic environment.
Moving right along to Section 2. Meet the cosmic twins.
As it turns out, these clusters aren't completely identical. Actually, scratch that. Think of them more like fraternal twins. On one side, we have NGC 869, also known as Ash Persei. On the other side, we have NGC 884, or Chi Persei. They're categorized as Trumpler type I3R and are both about 13 to 14 million years old, which essentially makes them teenagers in cosmic terms. But here's where they differ. NGC 869 is the heavier, more tightly packed sibling, weighing in at about 3,700 solar masses. NGC 884 is slightly less dense and a bit lighter, sitting at roughly 2,800 solar masses. But despite those differences, their shared origin is totally undeniable.
And looking at the visualizations here brilliantly illustrates that shared origin. These Gaia data release 3 charts, specifically the proper motion and convergent point diagrams. They act as the kinematic fingerprints of the stars. And you definitely don't need a PhD in astrophysics to see the patterns here. Just notice how the data points for both clusters clump together dynamically. The fact that their proper motions, their physical movements across the sky, are so tightly aligned proves beyond a shadow of a doubt that these clusters are on a shared cosmic journey, co-moving right through the Milky Way together.
Which brings us to Section 3. Inside the stellar cores.
But what happens when we zoom in from those macrogalactic movements and look directly into their dense, bustling centers? Well, notice how the graph here reveals their internal dynamics. The lines representing the heaviest stars curve upward way more steeply near the center compared to the lighter stars. This is showing us early mass segregation. Essentially, the heaviest stars are sinking toward the center of the clusters while the lighter stars are being pushed out toward the edges. And because these clusters are so young, seeing this indicates some incredibly rapid internal evolution.
The absolutely crucial takeaway here is that these cores are intensely violent environments. Just to give you a rapid-fire breakdown, the core of NGC 869 is twice as dense as its twin. Both of them contain these massive, highly volatile B-type supergiants. We're talking stars over 30 times the mass of our Sun. Based on the mass we see today, astronomers estimate that roughly 40 massive supernovae have already detonated right in their centers. To put that into a familiar context, the total stellar mass here is 8 to 10 times greater than the famous Orion Nebula cluster. These aren't just pretty little jewels, they are absolute stellar heavyweights.
Okay, let's jump into Section 4, Revealing the Hidden Halo.
Now, as massive as those visible cores are, the naked eye view, it really only tells half the story. For decades, we thought the dense cores we could see through our telescopes were the entirety of the clusters. But recently, the European Space Agency's Gaia Space Observatory stepped in like a cosmic detective. By precisely tracking the microscopic movements of millions of stars, Gaia uncovered a massive secret extending far, far beyond the visible boundaries of our twins.
Check out this kinematic histogram. The peaks you're seeing represent the speeds of the stars. What this data reveals is that there is a vast, extended halo population of stars that completely belong to the clusters, but they're located way outside the central cores. We are talking about a massive, low-density halo structure stretching out well beyond 1 degree from the cluster centers. And the sheer scale of this hidden structure is staggering. The filamentary substructure of this halo extends over 200 parsecs, or roughly 650 light-years away from the center. I mean, that is an enormous footprint in space. What this tells us is that the birth of these clusters wasn't just some simple, localized collapse of gas. Their formation was a highly complex, large-scale event. It was likely triggered by shock waves from ancient supernovae, or maybe the collision of massive molecular clouds.
And finally, Section 5, the future of Caldwell 14.
So, now that we understand where they came from and what they really look like today, let's zoom all the way out to the galactic scale. As they hurtle through the Milky Way side by side, we have to ask the ultimate question here. Are these fraternal twins actually gravitationally bound to each other? Like, are they gonna stay together forever?
Let's break down the math from the latest research. The current physical separation between the centers of the two clusters is about 103 parsecs. However, when we calculate their gravitational reach, their combined tidal radius, it only extends about 26.14 parsecs. So when you divide the separation by the tidal radius, you get a ratio of about 3.94. And since that number is well above 1, it reveals a slightly melancholic truth. Despite their shared birthplace and their shared journey over the last 14 million years, they are physically too far apart to hold on to each other gravitationally. They're co-moving, sure, but they are not bound.
So what does that mean for their long-term future? Well, these beautiful, intricate patterns here simulate the 3D orbital tracks of both clusters around the galactic center over a 1 billion-year integration. You can see they follow very similar, nearly circular, low-eccentricity paths through the galactic thin disk. They're both just kind of bobbing up and down slightly as they orbit the massive center of the Milky Way, maintaining their parallel, shared journey, at least for now.
So if we summarize their entire lifespan on a timeline, 14 million years ago, they were born together in the gas-rich Perseus spiral arm. Today, they're co-moving through space 103 parsecs apart, beautifully lighting up our night sky. But the orbital modeling shows something completely fascinating. Because their orbits aren't perfectly identical, about 11 million years from now, these two clusters are scheduled for a potential dynamic interaction. They are going to cross paths again, potentially altering each other's structures forever.
Which leaves us with this final thought for today. The night sky often feels so permanent and unchanging to us down here. But as the data on Caldwell 14 clearly shows, the universe is incredibly dynamic. It is alive. Just imagine looking up at the Perseus arm 11 million years from now. When those massive clusters interact, how will the jeweled handle of the sword have changed? Will they tear each other's halos apart, or will they simply pass like ships in the cosmic night? It's just an amazing reminder that we are only witnessing a single, beautiful frame in an ongoing cosmic movie. Thank you so much for joining me for this explainer. Keep looking up and keep asking questions.